One, two, three. So, good morning. The last class we have seen the implementation of CMOS gates, actually gates which include both the pull-up and pull-down network made of MOS transistors, either P-type or N-type MOS transistors. So actually we have gates in which we have a pull-up network which can be composed by one or more PMOS switches, and a pull-down network which is composed by one or more NMOS switches. This structure is also called CMOS. CMOS gate, and is also called a totem pole structure. A totem pole structure, that means a structure that provides a connection of the output of the gate either to the supply voltage when high output level is to be forced, or to the ground voltage when a low logic level is to be forced. Actually, this type of gate has many advantages, since both at the high logic state and at the low logic state, the output is driven through the on resistance of CMOS transistors, which can be very low. So it behaves as a voltage source either at the low state or at the high state with a very small internal resistance. Very small internal resistance, which is positive, since as we have discussed, the resistance, the equivalent resistance at the high or at the low state is related to delays. So the smaller the resistance, the faster is also the gate. By the way, this structure, in spite of these advantages in terms of delay, the fact that the output is a good voltage source both at the high and the low logic output level, it has one problem, one important problem, in case we want to use shared interconnects. What is a shared interconnect? A shared interconnect is also known as interconnect, as a bus structure, is a single wiring, a single wire that should be connected to possibly different digital outputs. What happens at the electrical level when we have CMOS gates, when we have totem pole gates, which work as we have just discussed, and we want to connect the output of these gates to a single shared interconnect. So suppose that we have, for instance, two gates, one inverter here, and another inverter here, and we want to use the same shared interconnect, the same bus, to carry the information related to two digital modules that are to be connected to the same bus. Okay, since in a totem pole gate we have basically two switches that connect either the output to the supply or to ground, and this is true for both the gates. Basically, if we have that both the outputs connected to the same shared interconnect are consistent in terms of output logic level, so for instance, if we have 1 and 1 like this, okay, there is no problem. But once we have one gate at one logic level, so suppose that the first gate forces the output high and the second one forces the output low, so the pull down is on. Well, basically in this case, we are establishing a very low impedance path, basically a short circuit between the power supply voltage and ground, something like this. The equivalent resistance, we should not forget that from the electrical point of view, here we have a battery, basically. We have a battery VDD, which is connected in this way. When we have one gate at the high level and the other gate at the low level, we are establishing a low impedance path, since the on resistances of the pull up network of the first gate and of the pull down network of the second gate are quite small. We have that the current, from the electrical point of view, this structure is equivalent to the battery with these two small resistances are on and are on in series. The equivalent resistance is about 2 R on, and the current drawn from the supply, IDD, is VDD divided by 2 R on, and for R on tending to 0, as it is the case for transistors in the on state, we have that the current drawn from the supply tends to infinity. So it's very large. What happens in practice is that such a large current may damage the structure of the gates and lead to permanent damages. For this reason, we cannot use gates that are characterized by two network of switches at connecting the output either to the supply or to ground. That is the typical case of CMOS gates that we have discussed so far, and actually this structure is called totem pole structure, in which we have two a pull-up network and a pull-down network, both made of switches. This structure cannot be used for digital gates whose output should be connected to the same shared interconnect. If we have to drive a shared interconnect, we need to devise other solutions. And in practice, there are two solutions that can be adopted. The first solution is to adopt a so-called three-state output. In a three-state output gate, actually we have, as in totem pole gate, we have a pull-up network connecting the output to the supply, and we have also a pull-down network, pull-up, pull-down network potentially connecting the output to ground. But in between we have two transistors, a PMOS transistor between the pull-up network and the output, and an NMOS transistor between the pull-down network and the output, which are driven by an enable signal or its complement, not enable. Okay? So in this case, when the enable signal is high, the NMOS transistor that connects the pull-down network to the output is on, and the PMOS transistor which connects the pull-up network to the output, which is driven by whose gate signal is not enabled, is also on. So if enable is 1, this gate is equivalent to a totem pole gate with its own pull up and pull down network. Pull up and pull down network. And it provides a good connection either to the supply at the high logic level or to ground at the low logic level, exactly as it happens for the totem pole gate, for the standard CMOS gate. On the other hand, if the enable signal is 0, so if the enable signal is at the low logic level, we have that the three-state gate, basically both the pull up and the pull down network of the three-state gate are disconnected from the output by two open circuits. So we have these two open circuits related to these transistors which are off, that keep the external output Y disconnected from the pull up and pull down network. So in this case, the output of the gate, no matter what is the state of the pull up network or the pull down network, is in the high impedance state. So it means that the output is not connected neither to VDD nor to ground. Clearly, if we have two three-state gates that are connected to the same bus, the case that we considered before, so suppose that we have a bus and we have these two three-state gates, suppose that this is a three-state inverter. Actually, the symbol of a three-state inverter of a three-state gate includes these three these three horizontal lines close to the output. So if we have a gate and we want to specify that this is a three-state gate, we have these three lines close to the output, and then we will also have an additional signal which represents this enable. Clearly, this is the same is true for any kind of digital gate, for any kind of logical function. Okay, so what happens when we have a three-state gate connected, two or more three-state gates connected to the same shared interconnect? Here we have the shared interconnect and the two gates with their own enable signal. In this structure, provided that there is an external digital network that is called bus arbiter, that provides the enable signals to the gates and ensures that just one gate is enabled and all the other possible more than two are not enabled, just one and one, all the others and so let's call this N0, N1, N2, N3, for instance. So this is N0, this is N3. All the others should be low. If we make sure that this additional network that increases the complexity of the system provides just one enable signal for all the different gates active at the same time, we have that just one of these gates is connected to is physically connected to the bus, to the shared interconnect. So basically its output will be either low or high depending on the logical function that is performed. All the other gates instead, in particular this one which is highlighted here, are not enabled. That means that the two switches that connect the pull-up network and the pull-down network are open, so the output is in a high impedance state and does not affect the voltage, the operation of the bus, is in practice disconnected from the bus. So even if the pull-up network of this gate here is forcing a high logic level, since we have that the gate is not enabled, the output of the gate remains in high impedance and it does not affect the bus. In this case, in this example, we would have that the logical level of the bus would correspond to the logical level of the gate which is active. So in this case, the low logic level. Okay, so these are the symbols of this specific case highlighted here is three-state buffer. That means that the logical function which is implemented is y equal to a, that is the output logic level is equal to the input logic level. In the example which I have presented before, we had a three-state inverter in which the output was the complement of the inverter, but clearly we can use the same approach for all possible functions, okay? Actually, as I have mentioned before, for three-state gates, the symbol is completed by these three horizontal lines, okay? Actually, this is what I have just explained for the three-state inverter. We have these two additional switches here that are driven by the enable and enable complement signals, which either connect or disconnect the output from the pull-up network and from the pull-down network. Okay? Now, there is also another type of solution alternative to both to totem pole gates and to three-state gates that can be adopted. Basically, which are the advantages and disadvantages of three-state gates? The advantage is clearly that thanks to the additional switch, it's possible to connect three-state gates on the same bus, on the output of three-state gates, the same bus, on the same shared interconnect. Since we have that when enabled, three-state gate has also a low impedance both at the high logic level and at the low logic level, like a totem pole network, so it's suitable to drive the bus both at the high logic level and at the low logic level with good electrical characteristics, that is a low impedance both at the high and at the low state, which is a positive feature. On the other hand, as we have mentioned before, since when we have a shared interconnect, we need to provide these enable signals for the three-state gates. This increases the complexity of the system. Each gate has an additional enable input, and most important, we need an ad hoc circuit which manages the state of the bus and provides the enable signals. Actually, there is also another solution that is basically reduces the cost of the system, even if it leads to slight degradation in performance. The solution, the alternative solution, is the so-called open drain output. What is a digital gate? How does it work? A digital gate with an open drain output. Basically, a digital gate with an open drain output is characterized just by a pull-down network, as it is the most common case, or in alternative, just by a pull-up network connected to the supply, like this. Okay, so we have our open drain gate. The symbol for the open drain gate is a small diamond close to the output, and we have a single pull down network or a single pull up network connected either to ground or to the supply. Clearly, this gate is similar to the half CMOS gate that we discussed introducing CMOS gates, like this, in which we have just the pull down network or just the pull up network. So we have already discussed that basically these structures make it possible to force just one logic level. When the output should be, in the first case, when the output should be low, we have that the gate is equivalent to a low impedance connection to ground, which effectively forces V out equal to 0, so the low logic value, while this is at the low output state. When we have the case, the complementary case, when the output should be at the high state, well, in the three-state gate, we have simply the off. In the open drain gate, we have simply an off switch that basically does not force the output, cannot force the output Y high. So when we should have one state, or basically when the pull down network is not active, pull down not active, we have that the output is in a high impedance state. Clearly, if we want to use this gate as a true digital gate, suitable also to force a high logic level at the output, we need to add something externally that forces the high logic level, and this is the pull-up resistor. If we connect externally to the gate a resistor to the power supply, when we have this switch off, we have that the output, when the pull down is not active, thanks to this resistor which is connected between the output and VDD, the output voltage is equal to VDD, which corresponds to high logic level. The complementary case, in which we have just the pull-up network, which is less frequent, is the open drain gate is suitable to force just the output high. When we have to force the output low, we need to add a pull down resistor, which, when the pull-up network is not active, forces the low logic state. Actually, it's quite straightforward to observe that there is no problem in connecting open drain gates to the same shared interconnect, that is, to a bus. Suppose we have two open drain gates like these, two open drain gates that are characterized by just the pull down network. We can connect them on the same shared interconnect without any problem, because basically when we have that one of these gate forces the output low, clearly the bus is forced low. If we have both the gates forcing the output low, the output clearly is low. And if we have just one gate forcing the output low and the other in which the pull down network is not active, so the other is in high impedance state, there is no problem. The bus is driven low by the only active gate. Clearly, if all the gates are in the pull down network of all the gates is not active. So when we have all the gates in the high impedance state, the bus is also in the high impedance state. If we want to make sure that in this case the bus is not in a high impedance state but is at a high logic level, we need to put a pull-up resistor between the bus and the supply voltage VDD. You can observe that just one pull-up resistor is sufficient for all the gates, for all the bus. We don't need a single pull-up resistor for each gate. It's sufficient to have one pull-up resistor for all the gates connected to the bus. In this case, when we have the situation which is depicted here, all the open drain gates at the high level, actually, thanks to the pull-up resistor, we have that no current flows through the pull-up resistor since all these switches are open. The voltage of the bus is equal to VDD, Kirchhoff voltage law. We have V bus is equal to VDD, since the voltage drop across the resistor is 0, and so the logic level of the bus is 1. It can be observed that the actual logical level of the bus can be regarded as a logical, is related to the single outputs of the single gates. Let's call these X1 and X2 by a specific logical function. If we consider the truth table, the bus state is a function of the state of X1 and X2, 0, 0, 0, 1, 1, 0, 1, 1. Clearly, when we have at least one of the gates which force a logical 0, we have also a logical a low level, a low voltage on the bus and a low logical level on the bus. So we have case 0, 0, we have that the bus is low. In case 0, 1, even if we have just one of the gates that are connected, one of the open drain gates that are connected to the bus, which are active, we have that the bus is at a low logic level, even if we exchange the gates. When we have all the gates which are in the high state, that actually means for the individual gate high impedance state, thanks to the pull-up resistance, we have that the output level of the bus is high. So basically, we have that the state of the bus is given by the end of X1 and X2. Since this is a logical function which is not implemented by a single gate, but which derives from the interconnection of the different gates, this is called wired AND. The state of the bus is given by the AND of the corresponding logical state of the outputs of the gates, the open drain gates connected to the bus. Okay, so actually these open drain gates make it possible, can be connected to shared interconnects without any problem. Actually, when we have one of these gates is at the low state, the current flowing through the power supply in static conditions is not zero. This current will be VDD over the value of the pull-up resistance. So we cannot choose this pull-up resistance too low, otherwise we will have a large current drawn from the supply. And also, if we consider the on resistance of the gate, we have that the output voltage that is given in this case, since we have the voltage divider between the pull-up resistance and the on resistance, we have basically that V out is VDD times R on over R on plus R PU. If we choose R PU very small, clearly we want that at the low state, this is at the low state, this should be as close as possible to zero. But if we choose a small value of RPU that is comparable with R on, this can be significantly, this factor can be significantly different from zero, and so we can have that the low logic level VOL can be different from zero. Okay, this is a disadvantage. We have a degradation of the low logic level. But on the other hand, if we choose resistance, pull-up resistance, which is not very small, we have that the effective resistance that we have, that this gate shows at the high logic level, so the one which is not forced by the switch, by the pull down network, but is forced by the pull-up resistor, is much larger than R on. Okay, so actually we have that at the low logic level, the equivalent circuit is 0 volt with resistance Rn, the on resistance of the pull-down network, that is quite small, while at the high logic level, the equivalent circuit is actually is not 0 volt, but is VDD times R on divided R on plus RPU, as we have calculated before, which actually should be close to zero. And at the high logic level, instead, the open circuit voltage is VDD, but the equivalent resistance is, when this is off, the equivalent output resistance is the resistance of the pull-up resistor, is the pull-up resistor resistance. Okay, so it follows that R RPU, since RPU needs to be much larger than R on, this equation in terms of equivalent resistance at the low and at the high logic level is very asymmetric. So at the low logic level, or in general the logic level which is forced by the pull up or down network inside the open drain gate is low. So at the low logic level here we have low internal resistance, while at the high logic level we have a much higher internal resistance. This will have a significant effect on the delays. We have calculated the delays, the transition from 1 to 0, or the transition from 0 to 1 will be very different when we use open drain gates. But this will be discussed in more details in the next video. Thank you for your attention.